layer cells. By thin, we're trying to work down to about 10 nanometers, and we've got measurements on cells consisting of 2 gold electrodes separated by about 30 nanometers. And so I'm going to tell you a little bit about the experiments and a lot about the expectations. And I want to congratulate Deborah. So I was thinking during your talk, it's really easy to make complex nanostructured materials, but it's much more difficult to get electrons out at high energies and do something useful with them. And you do a great job without burning up the system or having it crumble. So just wonderful science over the years. Many years ago, this is a long time ago, I was involved in the genesis of a project at the Office of Naval Research along with Deborah and Jeff Long and Bruce Dunn, and led by Rich Carlson, I think, or Bob Nowak, I'm not sure, Nowak. And it was over a beer after a meeting one day, talking about, it must have been Bob Nowak to come up with this idea, about batteries, very high energy batteries that could be recharged with photons. And it was just a great idea. I thought this is really spectacular. And there was a MIRI put together, 3 or 4 universities and Deborah's group, to try to make 3-dimensional battery structures, to come up with new architects. I mean, this is really new stuff, and it was science fiction at the time, and you've seen Deborah's made a lot of progress. And the basic goal was to fabricate very high density, energy density batteries without trading off the power. And I don't want to get into the details and talk about that today, but one of the designs was this that you just heard a little bit about, this gel microstructure, nanostructure battery that Deborah and Jeff have worked on for a number of years. And there's an anode that's coated with a very thin polymer film, which acts as the electrolyte, and then you back diffuse lithium metal into it, and you hook up a wire, and it probably burns up still. What does it do?
It's like doing molecular electronics.
But it's a fantastic idea. Even if it hasn't been perfected, it's a marvelous idea because you get very high energy. If you go through the calculations, very high energy density, but because the electrolyte thickness is very thin, on the order of 10 nanometers or so, these were conformal electrodeposited polymer films, the power stays at a very high level. And you don't have to use very conductive polymer films because they're so thin. It doesn't matter if they're resistive. The thinness gets you over that hurdle. And looking at this, I started thinking about, well, we all started thinking about this. What would happen if you really did have 2 electrodes separated by 10 nanometers? And the electrodes are charged, and the electrical fields from those charges are going to be overlapping, and they're going to influence transport, and they're going to influence the kinetics of ion insertion into the electrode materials. And so we started a calculation. This has been a good 15 years ago, of modeling a closed thin layer electrochemical cell. And it's closed in the sense that ions can't get in and out. You start with so many ions, and that's what you live with as you charge or discharge the cell, because that's how a battery really works. It's not an open system. And then the goal is to compute or to understand the current voltage response of such a device as you make the electrolyte thinner and thinner and thinner, getting down into the nanometer range. What will happen? The physics is very, very simple. We're just worried, initially at least, with the overlap of the electrical double layers between the 2 electrodes. So if I have a cell thickness D up here, I'm going to have an electrical double layer at both interfaces, or the concentration profiles and the potential profile. And the thickness of these electrical double layers is characterized by the Debye length. The Debye length is not a function of the thickness of the cell. So you have 2 characteristic length scales that you have to compare here. The thickness of the electrical double layer relative to the thickness of the cell. And when the thickness of the cell is much larger than the Debye length, then you just have ordinary electrochemistry, 2 electrodes separated by infinity for all practical purposes. But if you can push the electrodes together, and just to calibrate you, the Debye length in 10 millimolar KCl is 3 nanometers. So if you can push these electrodes, say within 20 nanometers of each other, they should sense each other in terms of the electrostatic potential. And that's going to affect the transport, but it's also going to affect the kinetics, electron transfer kinetics, or ion transfer kinetics at the interfaces. Okay, so no ions in or out. This is a different type of cell. If you heard Serge Lemay's talk this morning, he was talking about 30 nanometer wide cells. But those were open cells where the electrolyte ions and the redox molecules can come in and out. This is a closed system, and that's the key, a key aspect of this work. Okay, so what do you expect for the electrical potential profile? Well, if you just think about decreasing the concentration of lithium chloride between two electrodes, so starting at 1 molar, 2 electrical double layers, well separated, then you start decreasing the ion concentration, and eventually you get to something that looks like a capacitor. If you take all the ions out, it's simply a capacitor with a linear potential profile, right? That's not what we're doing here. What we're going to do here is keep the lithium chloride, or the electrolyte concentration, constant, and we're going to decrease the width of the cell. And if you do that, you get exactly the same pattern of electrostatic potential profiles, because as you push the electrodes, if you keep the lithium chloride concentration constant, say at 100 millimolar, and you push these electrodes together, what's going to happen is you're going to run out of ions to screen the charge on the metal surface. So even though this case over here corresponds to 10th molar electrolyte, you'll end up with this capacitor-like electrostatic potential. Okay? And that's sort of the model of what's happening in Deborah's sponge battery, where you have these very, very thin electrolytes that separate two metal electrodes. Okay. All right, if you calculate the potential profile, this is voltage or potential versus distance for a cell that contains 10 millimolar potassium chloride. These are real calculations. And I'm plotting the distance across the cell normalized to the thickness of the cell. That's why they all look the same. But a very wide or large cell, 500 nanometers, is this one right here. The green curve comes down, and it's over here. This is the Gooey-Chapman limit. As you make this cell thinner and thinner, eventually down to 5 nanometers, you approach this linear potential profile that just corresponds to a capacitor. But keep in mind, I'm keeping the electrolyte concentration constant throughout these calculations. Now, these look like just PowerPoint, like I drew them this morning with PowerPoint. These are real calculations. And I'll just show you one. We can't, the limits, the Gooey-Chapman limit, I can test to see if it's correct. And the linear potential profile I know is correct because there's no other answer. But the other solutions don't have analytical closed form comparisons that I can make here. But I can compare the results for a very wide cell. This corresponds essentially to the electrical double layer at one electrode. And the simulation results are the lines. These are for different concentrations of potassium chloride, and then the dots are Gooey-Chapman theory. And I just show that to try to establish some faith in Mark Whiteman sitting here on the front row who says, I don't believe any of this. That in fact these simulations do, when we can, we compare them to analytical expressions. Okay. So now the electrochemistry, that was the potential profile. The electrochemistry is the same cell. We're going to have redox species, the oxidized and the reduced form, and here are the equations, the redox chemistry. I'll go through one of these in some detail. I don't want to get into too much of a description of the calculation. You do have to put in a plane of electron transfer at these interfaces that corresponds really to the closest approach to the redox molecule. You have to put that in and then put in a reasonable dielectric for the solution adjacent to that charged metal surface. So for water, it's about 5 or 6, and we use that. If you don't put that in, you get totally unrealistic electron transfer rates because the concentration of the ions is way off. Right? So we put that in, and then we do the calculations are Butler-Volmer for the electron transfer, electrostatics at Poisson everywhere through the cell, and then transport is Nernst-Planck. Now, if for such thin cells, you might ask the question, I get asked this all the time, why are you doing continuum-based calculations? If it, you really got to be doing this at a much higher level. And in fact, we are. We're collaborating with Greg Voth, who's at the University of Chicago, who's a theoretical chemist. We just published a paper recently, and I won't go into this because this really is his work along with his postdoc, Matt Peterson's work. But these are kinetic Monte Carlo molecular dynamics simulations of exactly the same problem that I just described to you, right, where you have solvent, a few ions, you start pushing the electrodes together, and you calculate the current flow resulting from the molecule diffusing back and forth, shuttling back and forth between the electrodes. And when you do that, you clearly see enhancements in the transport and variations in the electron transfer rate resulting from the overlap of the two electrical double layers. Right? So that's another approach to that. But we're doing more continuum-based calculations and experiments. I actually believe the experiments more than the calculations for once. Okay. All right, so we're going to decrease. So what happens when you decrease the thickness of the cell in terms of the current flow? And so we've calculated, I'm going to show you current voltage curves here, but this is for lithium coming out of the right electrode, positively charged, transported across the cell, and then it's disappearing over here. All right, here's the cathode. And here's the electrical potential profile. This is for a very thick cell, 800 nanometers in width. This is the electrical potential profile. These are the concentration profiles. You pretty much have electroneutrality all through the cell except at the edges where you expect the double layers to exist. All right? And there's a concentration gradient. The lithium is being driven primarily by diffusion from the right over to the left. Right? If you decrease the thickness of the cell down to 20 nanometers, you get something totally different. First of all, you get a linear potential profile, so the electrical double layers are completely overlapping in this limit. And if you look at the lithium profile, concentration profile, remember lithium's coming out of the right, going to the left, there's no gradient. So 20 nanometers, what's happening here is the transport of the ions is being completely driven by the charge on the electrode surface, and diffusion doesn't play a significant role. It was a very surprising result. Right? And I still don't know if I've got a really great explanation or way to describe that. Here are the current voltage curves for this is normalized current versus voltage, 0 to 100 millivolts. So this is a voltage we're applying to the cell. Here's the diffusion limited current, the sigmoidal shaped curve. If you start pushing the electrodes together, what you see is this curve starts to straighten up, go down to 5 nanometers. And at 5 nanometers, you reach the asymptotic limit of all this mess. Right? And what's interesting is that at 100 millivolts, the current has increased by a factor of 4. So it makes this interesting in thinking about making cells thinner and thinner for energy applications. But let me tell you the truth here. These calculations correspond to the charging of a battery, lithium-ion battery. And what they would say is that the overlapping double layers greatly enhance the rate at which you can charge a lithium-ion battery. But if you do the calculation for the reverse chemistry, the discharge of the battery, you get just the opposite effect. Instead of the current being enhanced by a factor of 4, the electrical fields just nail the current and essentially goes to 0. Okay? So the message here is as you make cells, as you make them thinner and thinner, some very unusual transport behavior results, right? And we've been trying to now demonstrate this experimentally. Actually, I've got a few more calculations here for this redox couple, 3 plus 2 plus in a cell. Here's the current voltage curve you expect for electrodes far apart. And then as you push them together, this is 200 nanometers down to 5 nanometers. What you see are these odd-shaped curves. And as you go to high potentials, either positive or negative, the current goes to 0. So why does the current go to 0 here? And the answer, well, first of all, we'll look at potential and electric field distribution. So here's the electrical potential. Here's the field. The fields are very high, but they're not off-scale high. They're typical of what you would expect for electrical double layer. But when you put those redox ions in such a narrow little cell, what happens is they all move to one side or the other in response to the electrical field. And you get curves. These are concentration versus distance in the cell. And this is the applied potential, all right, for this reaction here. And so this side over here corresponds to this electrode. If you apply positive potential to this electrode, what you end up doing is sucking all the redox ions out of the cell, putting them across on one side of the next to that electrode, and there's none at the right-hand side necessary to balance the current. And therefore, the cell current in a two-electrode system without any external ions coming in to balance or shield the electrodes, the current goes to zero. Okay? That's a simulation now. Okay. All right, so we've been building these cells, trying to build them. This is a very hard problem. Two gold electrodes separated by, say, 30 or 50 nanometers of solution. We use aluminum oxide as the walls of the beaker here, and aluminum oxide is deposited by atomic layer deposition. And then we've had a hard time figuring out how to make a closed cell, put the solution in a closed cell. That's the bugaboo of all of this research, all right? If you have an open cell, you can use microfluidics to pump stuff in, but in that case, ions have access to the solution. They can move in and out, and it's not the same problem that we're trying to study. So what we do is we build the bottom part of the cell, and then we take a piece of PDMS, fairly thick, and we glue a sheet of mica to that, and the mica is about a micron thick. It's basically saran wrap, or thinner than saran wrap, and deposit gold on top of that. And the gold, both these gold electrodes are ultra-smooth electrodes, right? And then you take this PDMS stamp with the gold on it, and you just push it, you press it down, and you do the best you can do. George Whitesides is going to give you a better idea after this lecture on how to do this. Okay. So the insulating walls are aluminum oxide, and I love this. It's just standard ALD of the aluminum oxide. We go down to about 15 nanometers, but here's a capacitor of that cell. It's just two gold electrodes separated by aluminum oxide. And for this geometry, 2 by 2 nanometers, you expect a tera-ohm resistance. You measure the current voltage curve, and it's right on tera-ohm resistance. And that's important because you don't want the walls of your cell shorting out the redox chemistry. And then we define, the electrodes are lithographically defined. This is pretty straightforward stuff. So here's a gold electrode. Here's an optical image of the gold electrode. We make different sizes here. If you just take that electrode, this is shown in cross-section. Here's the gold, here's the aluminum oxide, and then there's a little region here that's exposed. And you do electrochemistry on it. It's very well behaved. This is the oxidation of ferrocene, and then there's a simulation on top of it, and it agrees perfectly. So these are nice, clean gold electrodes. All right, so here's the big problem. Putting a drop of fluid in this little 30 nanometer thick cell. And the best syringe we have, which is unbelievably expensive, is like a nanoliter syringe. All right? But the volume of this cell is 10 to the minus 14 liters. So this PowerPoint drawing is the biggest lie in the world. All right? It's like trying to fill up a cup of water here using a drop the size of the room, to put it in perspective. But we do our best. We do this, and we use various ways to get rid of the excess solution, and then we press, and we know we have solution between the top gold electrode and the oxide film. All right, it's like an old Charlie Reilley thin layer cell that leaked. Okay? All right, so here's electrochemistry. The solution contains ferrocene and ferrocenium. All right, and it's you scan positive, you get a wave scan negative. It's perfectly symmetric. And the one thing I didn't tell you, but maybe I don't need to tell you, is that if you have two gold electrodes, no matter what you put in between them, doesn't matter what the solution is, you must obtain a symmetrical current voltage curve, symmetrical around the voltage axis and the current axis. All right? If I scan positive on the top electrode, that's equivalent to scanning negative on the bottom one, vice versa. All right? And this is nice and symmetric. It's slopey. That's okay for the time being. All right? We got a lot of work to do in this experiment. But the magnitude of the current is about right based on the dimensions of the cell. So this looks like it's working reasonably well. All right? Now you go to a charge reaction, ferrocyanide, and this experiment is just at a gold disc electrode using a real reference electrode. So we're just measuring. The red here is looking at the oxidation of ferrocyanide, the reduction of ferrocyanide. This is in 2/10 molar electrolyte, potassium nitrate, and then you take the electrolyte out, and you see the curve. There's a shift in the potential. Forget about that. But there's a change in the limiting current here. So for the oxidation of ferro to ferrocyanide, there's a slight increase. And that's because when you oxidize ferrocyanide and you go from -4 to -3, that's equivalent to making a positive charge at the electrode surface in the solution. And that sucks in, through migration, the ferrocyanide reactant at a higher rate. Likewise, when you're reducing ferrocyanide, you see a decrease here for just the opposite reason. When you go from -3 to -4, you're creating an extra negative charge in solution, and that acts to repel the incoming reactant, so it slows it down. And there's a brilliant gentleman in the back of the room, old French guy, amateur, Italian, French, you go by either. A lot of us worked on this problem. Mark Whiteman worked on this problem, other people in the room 20 years ago. But the equation that really, in my mind, just kind of grabs everything is what I call the amateur equation, which predicts this decrease in the current or the increase in current when you take out the electrolyte. And for these two reactions, what you expect is this current should decrease by about 15%, and this one should increase by about 15%. And you see qualitatively the experiment matches up with the prediction from the amateur equation. All right? Now we're going to do, that's a microelectrode out in bulk solution. Now we're going to do the same thing in this tiny little 30 nanometer cell. Okay? And the first thing that grabs you here is, so here's the red curve is with electrolyte, and now you take the electrolyte out and boom. Instead of 10 or 15% increase in the current, you get a 200% increase in the current. And likewise up here, instead of getting a very small decrease in the current for the reduction of oxidation of ferrocyanide, now you see a huge diminishment here. All right? Curves aren't as pretty as we like. There's hysteresis here that I think is probably associated with some leakage along the top electrode. The current, the voltage, well, the whole wave shape is not symmetrical around zero. It's centered at zero. That's good. But the shapes of the waves are not symmetrical. So there's something going on here that we don't really understand. There is obviously clearly a big field enhancement here. Electric field, you take the electrolyte out, you see this massive migrational transport, the effect on the voltammetric shape. And I've drawn it this way. I've drawn the top electrode, a little buckled. We don't really know that, but I've drawn it just to throw that out as a possible explanation. Likewise, if you put ferrocene in, and you look at the oxidation of ferrocene, and you put ruthenium hexachloride, and look at the reduction of ruthenium hexachloride, this again is at a gold disc electrode. What you see is when you take the electrolyte out, there's no effect on the oxidation of a neutral molecule because it doesn't care if there's any excess charge at the electrode surface. But the ruthenium reduction is enhanced because, again, when I go from 3 plus to 2 plus, that's equivalent to creating a negative charge at the surface, and that enhances the migrational flux of the ruthenium-3. Okay, so you put this in the thin layer cell, and again, you get this spectacular enhancement in the electrical field-driven transport of the ruthenium-3 plus to the electrode. Okay, instead of being about 10%, now the current doubles. All right, and it's huge. All right, while the ferrocene stays unchanged. There's no effect on the ferrocene. Okay? In this case, the curve is not centered at 0. There's an asymmetry in both the voltage axis and the current axis. Okay, let me finish up here. Summarize. So for distances, for cell thicknesses less than 100 nanometers, the current in the closed cells is closed cells. That's key. None of this would happen if the cell was open. The closed cell is driven by high field transport. These ALD aluminum oxide layers are fantastic if you want to build stuff. Right? It's been wonderful, the best part of the experiment. And we still have a long ways to go to interpret and to improve the experiment. But we're making a lot of headway in the last few months. So thank you very much for your attention, and congratulations to several of us.
So in the setup where you can charge but not discharge, you can potentially create a system where a corrodible electrode wouldn't corrode.
Yeah, perhaps. But I don't care about corrosion. I've been down that road before. The DOE is too flaky.
Can we record that?
It is being recorded. But I think you're correct. I understand. George? Oh, sorry.
At these very short length scales, it seems like the voltages, even though they're not huge, could still lead to very large electric fields. And I wonder if there's any effect from electrophoresis of actual Coulombic attraction on any of the charged or neutral.
To me, electrophoresis is the same thing as migration of ions.
But in a field which makes a step in one direction more favorable than a step in
Yeah, I think the answer is yes. So I've been using different terminology to describe it, but yes.
This assumption that at very small distances you have a linear relationship connecting potentials to electrons. But isn't there the problem that the polarization of any molecules that is in there, anything, even in continuum, is nonlinear? Is going to mean that that's always going to be a nonlinear relationship?
We're assuming it's not a function of the field that's being applied. Absolutely. And what I didn't show, those simple calculations of the electrostatic potential where it's linear, I did not put in the region where you have dielectric saturation, which would make it nonlinear. It would still be linear in the bulk. It would change things quantitatively, but not qualitatively. Or I don't think it would, maybe.
Well, yes.
Okay.
In the back? You have to really speak up. If I can't hear, he can't hear you.
I was just wondering.
Why don't you stand up? It might be easier.
I think I can speak up
There we go.
loudly.
Now we go.
I was just wondering, when you cycle in several times, are they reproducible?
I'm being blinded by this light, this silly light.
When you
Say it again.
several times, are they reproducible?
Oh, in the experimental curve?
Yeah.
No, you know, the curves that have a lot of hysteresis, that hysteresis changes as you're scanning, but the magnitude, it basically is reproduced. It stays, it doesn't decay to zero or increase to a huge value. The shape of the curve is fairly constant. But with that much hysteresis, every curve's a little bit different for sure. Yeah.
I'm a little puzzled at your result with ferrocenium. I understand that it's neutral for the oxidation reaction, but the converse, the reaction at the other electrode, the reduction reaction, there the molecule is charged.
Absolutely. I'm a little puzzled by that result too. I skipped over it really quickly. I'm actually puzzled by all of the results, the interpretation of all of them. We're just getting to the point where things are reproducible enough to, and this effect, this what I call this amateur effect that we're seeing in the thin layer cells, that was totally surprising. We didn't expect that at all. But it looks like it's dominating the response of those two cells.
Right.
Royce?
Just a quick remark. The asymmetry that you see reminded me of this morning in nanopore discussions, when you have asymmetry that look a little like that?
My
Is there a
stuff?
connection?
My work this morning?
Yeah. No, not your work. It was,
Serge's, his, LeMay's talk?
yeah, yeah.
I don't remember. Right, Royce, we're getting old.
Does this also suggest that there is an optimal distance for batteries?
It depends on what type of battery you're making, what the use of the battery is. So if you want a battery that slowly discharges, but you want to charge it really rapidly, then the simulations would say make it really thin. And maybe it's a cell phone battery, right?
Fair enough.
Right? But for other types of applications, if you want high power on the discharge, then the simulations point you in different engineering directions.
One last question. If not, let's thank Ken Reagan.